Hi everyone, welcome to tutorial 7, Electrochem. Okay, now question 1, work out the oxidation numbers of the underlying elements. So as usual, I'm going to show a few of it, so the rest you can just try it out, maybe A, C, alternate E, and then G, and then I, right? So let's start with A. So MnO2. So what is the charge of or the oxidation numbers of manganese? Very simple. Manganese is unknown. All right. Plus with 2 oxygen, 1 oxygen is -2. So 2 times -2. Overall charge, top right corner, there's no charge. So equals to 0. So Mn equals to +4. So A is +4. C. Magnesium nitrate. Now this is obvious. All right. This is an ionic compound. So obviously the charge of magnesium is Mg2+, because 2 here and 1 here is actually for the nitrate. So we know that Mg is 2+, nitrate is minus. Yeah, so Mg is 2+ here. So the answer here is A is 4+ or +4, the oxidation number. C is 2 positive. All right, I think insufficient place. We continue. E. Okay, so ClO4 minus. So what is the charge of oxidation numbers of chlorine? So chlorine A plus with 4 times -2. Overall charge is -1. So chlorine minus 8 equals to -1. So chlorine equals to +7. See that? Chlorine is after phosphorus and sulfur, beyond phosphorus and sulfur, so they can have multiple oxidation states. So chlorine in this case is +7. All right. And then the next one is alternate, right? So next one is G. So G here is C2H6. Now, again, this is a covalent molecule. So we still have to assume that one of these is negative, one of these is positive. So in this case, carbon and hydrogen, which one do you think is more electronegative? Of course, carbon. So carbon will carry a negative charge. Hydrogen will carry a positive charge, right? So carbon, I have two carbon unknown plus 6 hydrogens. Hydrogen is assumed to be positive, right? Because it's less electronegative. So +1, that's the common charge of hydrogen. So equals to overall, of course, is 0. So 2 carbon equals to -6. All right. So carbon equals to -3. So that's the charge of carbon for G. And then last one will be I, SO4. Okay, let me erase that. Now, last one is I, alternately, SO4 2-. What is the charge of sulfur here? Sulfur plus 4 multiplied with -2, common oxidation state or numbers of oxygen, and the overall charge is -2 here. Okay, so S equals to -8 equals to -2, so S equals to +6. So the charge for sulfur in SO4 2- is +6. All right, so that's it for question 1, right? Okay, now question 2 is a bit time consuming here. You need to come up with the half equations for each of this before you actually get the overall equations. Let me show you one by one, all right? So oxidation half equations, I would say from here I can see that obviously SN2+ changes into SN4+. 2+ to 4+, definitely in oxidations. Then we're going to balance it. Now, tin, SN both 1 on each side, so it's balanced. So the only thing is the charge, 2 positive on the left, 4 positive on the right. So remember that we add electrons to balance charge. So in this case, we plus 2 electrons here. So both sides having 2 positive charge. That's the balance equations, balance half equations for oxidations. All right. So reduction will be NO3- to NO. NO3- to NO. All right. So let's see what we can do. Nitrogen is balanced on both sides. Oxygen is 3, 1 here, so we need another oxygen, another 2. So oxygen is balanced by water, so I add 2 H2O. Then I have to balance the hydrogen by adding 4H plus here, acidic conditions, right? And then I believe nitrogen balance, oxygen 3 balance, 4 hydrogen all balance. Now is the charge. So what is the total charge on the left? 1- 4+, so 3 positive on the left, 0 on the right. So 3 positive on the left, you need to add 3 electrons to balance it. So both sides having zero charge. All right. Now, in order to get a balanced overall equations, what you need to do is the electron must be balanced. So first equation here for oxidation, you need to multiply with 3. Second equation, you need to multiply with 2. All right. Once you got that, you will have, wait, let me change the color. You will have 3 tin, 2 plus 3, and then 6, right? And this one times 2, so you have 6. Electrons will be cancelled out. So 2, 4 times 2, 8. All right, and this one's 2, and this one is 4, right? So once you've done this, cancel out the electrons, whatever on the left, you put it on the left. So I have overall here, I just put it like that, 3SN2 plus, all right, plus 2NO3 minus, plus 8 hydrogen plus, no more electrons, forming 3SN4 plus, plus 2NO plus 4H2O. All right, so this is the overall reactions after we balance it. So first question done. Okay, second questions. Oxidations of half equations. In this case, I can see I minus is changing into I2. That's oxidation because from negative to 0. And to balance them, I need 2I here. All right, it's balanced. And then in terms of charge, I have 2 negative on the left, 0 on the right. So I need to put 2 electrons here to balance them, both sides having 2 negative. Okay, reductions is Cr2O7, 2 minus, changing into chromium 3 plus, right? So let's balance the element here, 2 chromium, 2 chromium. Oxygen, we have to add 7 water in order to balance the oxygen, 7 oxygen on the left and right. And then balance the hydrogen, we need 14 H plus. See that? Because I have 14 H plus here, 7 water. So balance it with H plus because of acidic conditions, and now it's time to balance the charge. So what is the total charge here? 2 minus 14 plus. Overall, you get 12 plus on the left. On the right, I have 6 plus. So I need 6 electrons here to balance the 12 plus. So both sides having 6 plus. Make sense? And then in terms of electrons, the first equation, I just need to times 3. You get 6 electrons so that you can cancel them out. Okay, let's do this. So times 3. So I have 6 iodide times 3, 3 iodine, and this one becomes 6 electrons. So electrons can be cancelled out now, and the rest you just put it on. So Cr2O7 2 minus plus 14 hydrogen plus 6 I minus, changing into 2 Cr3 plus 3I2 plus 7H2O. All right, so just put whatever on the left and whatever on the right, just put it back, just to cancel out the electrons. So second, done. Part C. Okay, part C, what do we have here? Obviously, reduction is Ag plus to Ag, so I do reduction first, Ag plus to Ag, because I'm plus to 0. And silver is balanced on both sides, just need to balance the charge, plus here, 0 here, so I plus electrons on this side, so both sides balance. Done. Oxidation will be this one, the remaining S2O3, 2 minus, change into S4O6, 2 minus. All right, let's try to balance them. S2O3, S4O6, so I just times 2 here. All right, then you get 4 sulfur, 6 oxygen. Elemental balance, done. And then electrons, I have 2, 2, 4, 2 times 2 here, 4 minus on the left, 2 minus on the right. So how to put electrons? Here, of course. So 2 minus, 2 minus, 4 minus, and balance on both sides. Now you will realize that in part C, no hydrogen ions involved. See that? It's supposed to be acidic conditions, right? Now, not necessarily to include hydrogen in it if you don't need it. So you don't have to show the H plus, because the acidic conditions could be something that involved in the reaction, like this one, part A and as well as part B. They are involved in this reaction. They are reacting and changing into water. But for certain acidic condition, the acid is actually acting as a catalyst. So not necessarily they must involve in the equations or overall equations. So like in part C here, we don't need to put in H plus to balance it. We can still get a balanced half equation. So that would do. So we can ignore the H plus. All right. And then now what we're going to do is we can balance the electrons, right? So 2 electrons on here, 1 electron. So this second equation need to times 2 in order to get 2 electrons, so that I have 2 silver ions, 2 electrons, and 2 silver solid. Electrons can be cancelled out now. Whatever on the left, put it back. 2s2o3, 2 minus, plus with 2 silver. Done. Electrons no more. Changes into, sorry, 2 plus. Changes into 2 silver solid plus s4o6, 2 minus. No more electrons. So that's a balanced equations. All right. And let's start again for part 4. Okay. So part D. Again, I see iodine, iodide, I minus change to I2, so it's oxidations. So I minus changes to I2. So balance 2I minus, and then to balance the charge on both sides, make sure it's 2 negative, I put 2 electrons here. Done. Reduction, ClO minus changes into Cl minus, right? And in terms of chlorine, it's balanced. In terms of oxygen, no. I have to put 1 water here, so to balance the oxygen. And then what next? Need to balance the hydrogen, right? So I have 2 hydrogen, so I put 2 H plus here. There you go. You have acidic condition, so you have free, you have sources of H plus. You can put it in to balance it. So we balance everything in terms of atoms. Now it's a charge. So what is the total charge on the left? ClO minus 2 positive, so you get 1 positive, and here is 1 minus. So you need to add 2 electrons on the left. Therefore, overall, you get 1 minus on the left, 1 minus on the right. See that? So this is reduction. Yes, electrons on the right, electron on the left, oxidation, electron on the right. You can double check with the rest. Okay, so the next part is to get an overall. 2 electron, 2 electron. Wow, just nice. You can cancel them out. And then you just put in 2I minus plus ClO minus plus 2H plus, forming Cl minus plus H2O. That's it. All right, that's all for the half equations and overall redox equations. Next, move on to calculations. Now, question 3. 23.3 ml sample of KMnO4 solution is decolorized by 0.1111 grams of oxalic acid. Formula is given. It's an acid. So the products are manganese and carbon dioxide. Now, obviously, you need to come up with the half equations and then the overall equations before you manage to calculate, because you need the mole ratio between manganate, KMnO4, and the oxalic acid. Without the ratio, you can't actually get the concentration. All right, so first we need to come up with the half equations. First, I have MnO4 minus changes into Mn2 plus. As usual, assign a product to each of the reactants. That's the first half equation I'm going to construct. So what next, guys? Mn manganese is balanced. Oxygen, I need 4, so 4H2O here. I need to balance by 8H plus then. And then everything's balanced, the charge. 8 plus, 1 minus, I get 7 plus. 2 plus here, so I need 5 electrons. You get 2 plus on both sides. First half equation done. Second half equations is for the oxalic acid. Okay, just write out H2C2O4, and it's changing into, that's the only product after the manganese, so changing into CO2. So I will expect, yeah, that's the equations. So it's time to balance. Carbon, I need 2, so 2 carbon dioxide. Then I have 4 oxygen on the right, 4 oxygen on the left. So in terms of carbon and oxygen, balance. Only hydrogen is not balanced, so how to balance hydrogen? Put in acid, right? 2H plus. It is an acid anyway, so you should have H plus. So then we are done with the balancing. Now is the charge. So where do I put the electron to balance the charge? 0 charge on the left, 2 positive on the right. See that? 2 positive on the right. So I need to put 2 electrons here. Oh no, sorry. I shouldn't put the electrons here. What am I doing? So 2 electrons should be on the other side, right? Because 2 plus here plus 2 electrons, you get 0, which is the same on the left-hand side. Yeah, electrons on that side. Okay, now I already have the half equations, it's time to get the overall equations. So is it balanced? 5 electrons here, 2 electrons here. So the second equation here, I need to multiply by 5. First electron here, I need to multiply by 2 in order to get 10 electrons, and we cancel them out. So let's put it in. So I have 10 electrons, 2 manganese, 16 hydrogen, 2 manganese, 8 water. And here I times 5, so 5 acid, 10 carbon dioxide gas, 10 hydrogen, and 10 electrons. All right, so electrons and electron cancel out. What else we can cancel? 16 hydrogen, 10 hydrogen. Cancel out, I still have 6 hydrogen here. Okay, let's put that on. 2 manganate plus 6H plus, all right, no more electrons, plus 5 oxalic acid, C2O4, forming 10 carbon dioxide gas plus 2 manganese plus 8H2O, and we are done. All right, so what is the ratio now from the overall equations? The ratio between them is, between oxalic acid and manganese, is 2 to 5. Okay, that's the important thing. Okay, now we can start calculating as usual the mole concept. All right, so if I have 0.1111 grams of oxalic acid, what is the mole here? 0.1111 grams over the molar mass of this oxalic acid, 2 plus 24 plus 64. Okay, 2 plus 24 plus 64, so total is 90. So 0.1111 divided by 90, you get the mole as 1.23 times 10 to the power of negative 3. So that's the moles of oxalic acid used. And based on the ratio, guys, 5 to 2. So I need to divide by 5 multiplied by 2 in order to get the mole of manganate needed. So divide by 5 times 2. So the mole of manganate here after the ratio is 4.94 multiplied with 10 to the power of negative 4. Okay, so 4.94 times 10 to the power of negative 4, you get the mole of manganate. So this is what we want. We have the mole, we have the volume. You can calculate the concentration. So 4.94 times 10 to the power of negative 3 equals to mv. V is 23.3, all right, over 1,000. So 4.94 times 1,000, all right, divide by 23.3, the volume of CaMnO4. So the concentration of CaMnO4 is 0.021 mole per liter. Done. So that's the answer for number 3. Okay, basically the same thing, just that we have to construct our own half equations, get the ratio, and then only we can get the answer. Okay, number 4. What volume of 0.05 mole per liter of CaMnO4 is needed? All right, so concentration of CaMnO4 is 0.05. To oxidize all bromide ions in 25 ml of acidic 0.2 mole per liter of sodium bromide, according to the following unbalanced equations. Okay, as usual, we need the half equation. Both, we need the overall equation to get the mole ratios. So MnO4 minus, the same thing like just now, you're changing to Mn2 plus. If you still remember, you can just put it in 8 hydrogen plus 5 electrons. All right, and then here is 4H2O. That's the half equation. This one. Next is bromide changes into bromine. So balance, I need 2 bromides. To balance the equations, I need to put 2 electrons here in terms of charge. So done. What is the overall equations? All right. Overall equation is, so this value you need to times 2, and this one you need to times 5 as usual to make them balance. All right. So I have 10 electrons. I have 10 electrons. Cancel out the electrons. Done. So here is 2, 16, 2, 8, and 5, 10. So without writing out the overall equation, because they didn't ask about overall equation, they just want the ratio, right? So I can actually straight away compare like here, whatever on the left. So from here, I can see the ratio is 2MnO4 minus plus with 10 bromide. See that? So the ratio is 2 to 10, which is 1 to 5. So once we got the ratio of these two, we can solve the questions. All right. So ratio is 1 to 5. So what is the number of mole of bromide used? 25 ml, 0.2. So 0.2 times 25 over 1,000. MV over 1,000, you will get a mole 0.005. Okay, so if this one is 0.005, you need to divide by 5. Right, so the mole of manganate is 1 times 10 to the power negative 3 or 0.001. Okay, divided by 5 is the same thing. So this is the mole of manganate. And what is the concentration? 0.05. Oh, nice. So you can get the volume now. 1 times 10 to the power negative 3 equals to 0.05, which is M. V is what we are looking for. Divided by 1,000, so times 1,000 over 0.05. So volume needed is 20 ml. That's the volume needed. Done. All right. Okay, number 5. In the electrolysis of lead-2 nitrate solutions, a current of 0.25 A flowed for 30 minutes. Calculate the mass of lead deposited. The same steps used. Number 1, Q equals to IT. You get the charge. I is 0.25. And time taken is 30 minutes times 60. You get seconds. 30 times 60 times 0.25. All right, you get 450 C. Okay, that's step 1. Step 2, we use 450 coulomb charge divided by 96500 coulomb charge. 96500 is for 1 mole of electrons, 450 for how many? So if you divide them, you will get the mole of electrons, which is 4.7 times 10 to the power negative 3 moles of electrons. Okay, second step, we got the electrons. And third step, we're going to write the equation. Here they're asking for lead, and it's lead-2. So half equation for lead is Pb2 plus 2E changing into Pb because they want the mass of solid, right? So this is solid. What is the ratio between them? 2 to 1. So what is the mole here? 4.7 times 10 to the power negative 3. So the mole of lead produced will be divided by 2. Then you will get 2.33 times 10 to the power of negative 3. That's the moles of Pb form. Okay? And that's not the answer, of course. You have the mole. So 2.33 times 10 to the power negative 3 multiplied the molar mass of lead. Okay? So what is the molar mass of lead? 207, guys. So times 207, you get the molar mass. You get a mass. So overall, the mass is 0.48 grams. So 0.48 grams of lead is produced from this information. Okay, so that's the answer for number 5. Okay, number 6. Now, this is slightly different questions. Number 6, they give you the mass. Okay, they give you the mass of copper deposited at the negative electrode. Using copper sulfate solution, current is given. They are asking for the durations. All right. So first of all, we need to calculate. I just random because you should familiar with the steps. So first, I will start with this, the mass, because I can calculate the mole of copper. Just go backwards. So 4.77 grams of copper divided by 63.5. That's the molar mass. 4.77 divided by 63.5. You get 0.075 moles of copper. Okay, and then that's the first step. Second step is you have the mass of moles of copper. You need to find out the mole of electrons. So copper 2 plus 2E. You're getting copper solid. And the mole here is 0.075. So what is the mole of electrons produced and pass through the cell? So this value times 2. So 0.15 moles of electrons. Okay, so third step, I have the moles of electrons. So how to get the mole of electron from the usual calculations? We always use the charge over 96500, right? Equals to 0.15, the mole of electrons. So this is the usual way. And then from here, we can get the charge. So 0.15 times 96500, you will get the C, which is the charge here, equals to 14475 coulomb charge. So that's the charge. And how to calculate charge? Q equals to I, T equals to 14475 coulomb charge. And what is your I? 0.76 multiplied with T, which is your second, equals to 14475. And then time a second, 14475 divided by 0.76. You get a time. So you get 19,046 seconds, 0.05 or 0.1 second. So this is the time taken. Unless, oh yeah, they want it into minutes. So convert this into minute, therefore you divide by 60, you get 317.4 minutes. Yeah, that's the final. Okay, so the three steps, you know what's going on. So let's take the informations, piece and puzzle here, and then to make up what you want and then put back into the formula, you can get the answer. Okay, number 7, an electrolysis of water for 40 minutes produced 50 centimeter cubic of oxygen at a positive electrode based on this equation. Good thing is they give equations. Okay, oxygen to electron is 1 to 4. That's the ratio. How nice, right? And if the molar volume, still remember molar volume is either 22.4 or 24. But in this case, because under experimental conditions, so they give the molar volume as 24.5. So we follow this. Okay. And they're asking what current must have been flowing. Let's use the existing informations to calculate what we can. So first of all, we have 50 centimeter cubic of O2. And if I use this divided by 24.5, which is the molar volume, I should able to get the mole. But this 25.4 is in liter, which is dm cubed. So I have to change it into the same unit where we have 24.5 times 1,000, right? So it's actually 24,500. So 50 divided by the answer, you should get the moles of oxygen produced. 2.04. 2.05 times 10 to the power of negative 3. So that's the moles of O2 produced. Okay, we got the mole now. And from the mole of oxygen, what will be the mole of electron that flow in the cell? Because we want the current. So you need to times 4. 8.16 times 10 to the power of negative 3. So that's the mole of electrons. After times 4, ratio is 1 to 4 here. So we got the number of mole of electrons. What next? We need to know the charge, right? So how to get a charge again? So it's the charge over 96500, the Faraday constant, equals to 8.16 times 10 to the power of negative 3. So from here, we can get the charge by multiplying it. So you get the charge is 787.8. That's Coulomb charge. And then Q equals to I, which is the current, T, which is 40 times 60. Oh, sorry. Okay. Times 60 equals to 787.8. Now that's equalized then. And then what happened is 787.8 divided by you get I equals to 0.33A. Okay, so that's the answer. Let's double check. Yeah, 0.33A. That's the current used in order to produce 787.8 current. And this charge is flowing through, hence you get this mole of electrons. From this mole of electron times 4, you get this mole of oxygen gas. From this mole of oxygen gas, you times the molar volume, you get this volume of oxygen gas. So this is going backward again. So that's how it works. Okay, number 8. A molten vanadium compound is electrolyzed using a current of this and this, during which 0.0634 vanadium was deposited. Calculate the charge on the vanadium ion in this compound. So we are not sure. Vanadium is a transition metal, and they can have different charges, different oxidation numbers. So what is the charge of this based on the information given step by step? This is a bit tricky, but should be fine. Again, guys, we calculate whatever we can based on the information given. All right. So first, we can calculate the charge, right? So 0.15 multiplied with 40 times 60. Again, 2,400 times 0.15. So you get a total charge here of 360 coulomb charge. All right. And then what next we can do? I get the charge, I can calculate the mole of electrons. So 360, now step 1. Step 2, 360 divided by 96500 always divided by Faraday constant. You will get a mole of electrons. So the mole of electron is 3.73 times 10 to the power negative 3 moles of electrons. So this is the mole of electrons needed to deposit all the vanadium ions into solid, right? Okay, what else we can do here? Calculate the mole. 0.0634. We need to know the mole of vanadium grams divided by molar mass of vanadium, which is 50.9. Okay, and you will get the mole of vanadium 0.0634 divided by 50.9. You get 1.25 times 10 to the power negative 3 moles of vanadium. Okay, V. Now, I have the mole of vanadium form, I have the mole of electrons. Now, I'll give you a scenario here. How to know the charge of the vanadium? A scenario is something like that. Mg2 plus 2E. You get what? Mg, solid, right? Al3 plus 3E. You get aluminium solid. What if you have vanadium N plus? N is unknown because we are not sure about, we are looking for N. So N plus plus what? N electrons. Am I right? 2, 2, 3, 3. So Nn forming vanadium solid. You see that? So N electrons forming 1 mole of vanadium. And how many mole of electrons in a case? 3.7, 3 times 10 to the power negative 3, forming 1.25 times 10 to the power negative 3 vanadium. So from this relationship, the ratio, we can calculate the N, right? So what I'm going to do is 1 divided by 1.25 times 10 to the power negative 3, all right? And then multiplied with 3.73 times 10 to the power of negative 3. Automatically, you get 2.99. All right, so N equals to 2.99 or approximate 3. So there you go. V is 3 plus. That's the final answer. So this is a scenario we can see the trend. If it is 2 plus, you need 2 electrons, you get the solid. 3 plus, 3 electrons. N plus, N electrons. And using this and the information we have here, electrons and vanadium, put it in, we can calculate, and we can estimate that. All right, number 9. Now, in electrolytic cell shown here, an iron nail is being plated with copper. So iron nail is going to be plated using a copper, all right, as a surface. So which object, the ionine or the copper bar, should be connected to negative? Now, since this is going to be plated with copper, which means this has to be negatively charged. Otherwise, how to attract copper 2 plus ions, right? So it has to be negative. So answer here is which object? Negative plus ionine to attract copper 2 plus ion so that it can deposit and form a layer of copper. Write the equations for the half reactions that occur at the cathode, which is negative, of the electrolytic. So at the negative or the cathode, what happened? Copper ion is being deposited on it, right? So for B is copper 2 plus 2E so that it converts into copper solid. So this is what happened at the cathode, reduction. All right. What about anode? Anode is where the copper 2 plus comes from. Not from the solution, but from the bar. Of course, it can be from the solution, but the purpose is not from the solution, it's actually from the copper bar so that it transferred to the nail. Otherwise, the solution will be used up at the end, right? So the opposite of it, so you need to produce copper 2 plus from the bar. So it's copper, solid, okay, changes into copper 2 plus and releasing 2 electrons. So it's the reverse of the first one. So this is for C, okay? The same thing, but just that one is changing to solid, solid changing to ions. Show on the diagram the flow of electrons both entering and leaving the battery. So the battery is here. We know that copper 2 plus is being attracted to the ion nail. Ion nail is going to provide electrons to it so that it can turn into copper solid. So the electron is here, flowing to the ion nail, flowing out from the battery. And what happened here is actually copper change into copper 2 plus by releasing 2 electrons, right? So it's actually replenished the electrons flowing out from the battery back to the battery. So that's the electron flow. All right. Number 10, electrolysis of a mixture of 1 molar nickel nitrate and 1 molar cadmium nitrate. Now, 1 molar means 1 mole per dm³, and this is actually a quite standard condition, which is dilute. All right, concentrated is not 1 molar. Concentrated can be a 5 molar and above, or 10 molar. So 1 molar is considered dilute. Dilute means you have a lot of water in it. Okay, so this one, I can give you hints, but I'm not going to give you answer. You're going to give me during the tutorial session. So what are the product produced at both electrode, anode and cathode, when you have nickel nitrates and cadmium nitrate? The hint or the key here is 1 molar is considered dilute solutions. Okay, dilute means a lot of water instead of high concentration of the metal ions. All right, remember that. Okay, 11. In the extractions of sodium metal, you're trying to extract metal, sodium. A molten mixture of sodium chloride and calcium chloride is heated to 600, and the diagram shows how it works. What is the name of the electrolytic cell used in the commercial productions of sodium? Is actually the same thing, electrolysis of brine. Like I mentioned, electrolysis of brine can be concentrated, or this brine here is referring to molten sodium chloride, molten brine. Brine is sodium chloride, all right, the salt. So only molten you manage to get sodium. Otherwise, you will always get hydrogen gas at the cathode. All right, only molten, because there's no hydrogen, then they have no choice but to discharge sodium ions into sodium metal. All right, it has to be molten here. Write the half equation for the reactions occurring at the anode. Now, based on the diagram, which one do you think is the anode and cathode? We know that sodium metal in the molten state, liquid, is produced at the cathode, right? So at the cathode is actually the production of sodium, sodium plus E, you get sodium liquid, in fact, because at high temperature. So it should be a molten sodium metal, which is coming up from here, from the iron. So iron here is actually the cathode, right? Negative. And what about here? Here is actually different, carbon electrode. See that? And you have bubbles releasing out from here. So what else in the solution that will be discharged at the anode? Other than sodium, then it will be chlorine, right? So chloride is going to change into chlorine, all right, by releasing electrons. So therefore, chlorine gas is produced. Okay, chlorine gas is produced. Now, if the current through the cell is 1.2 times 10 to the power of 4, okay, what is the maximum mass of gaseous product that will be evolved during the 4 hours operation of the cell? Yeah, the same thing, guys. Q equals IT, right? So I'm solving C now. Let's take some space here. All right. So I have Q equals to IT. So I have 1.2 times 10 to the power of 4. Wow, that's a big current. And then 4 hours, so 4 times 60 times 60 to get seconds. There you go. Times 1.2 10 to the power of 4. Wow, huge. Big value. 1728. Okay, 50. Okay, that's the charge. I mean, it's quite normal in an industrial process. This is the total charge flowing through the cell. And what else is even? They want to know the mass of the gaseous product, which is a chlorine. So later we're going to make use of this half equations, right? We need the ratio. So next, what are you going to do? You use these divided by 96500, right? Always to get the mole of electrons. So I'm dividing it by 96500. You get, of course, it's a huge value, 1790.7. 1790.7 moles of electrons. Got that? So from the equation here, 2 mole of electrons to the ratio of 1 mole of chlorine gas produced, right? 1 mole of chlorine gas produced. So 2 to 1 means you're going to divide by 2. So I'm going to divide that by 2. You will get the mole of chlorine. So you will get 895.3 moles of chlorine gas. They want mass, so multiply with molar mass of chlorine, 35.5 times 2, you get 71. So answer 895.3 multiplied with 71 molar mass of chlorine, you will get the total mass of chlorine gas produced, 63566 grams of gaseous product, which is chlorine gas here. Okay, so that's the answer for C. All right, I have no choice but to erase that. So yeah, let's continue with D then. Suggest reason why one of the electrode is made of carbon instead of ions. Now, why are we using carbon here? Because look at the product produced here. Chlorine gas is being released. If these were an ion instead of carbon, which is inert, iron is not inert, right? So if you have chlorine gas produced at 600 degrees C with iron, what do you expect to get? So the iron electrode will react with the chlorine to get iron chloride, all right? FeCl2 or FeCl3. Who knows, right? So to avoid this, therefore, we change the iron electron into carbon, which is inert. Okay, that's the reason why for D, you must be able to write it out in a proper sentence. All right, let's move on. E, explain why sodium cannot be produced by electrolysis of an aqueous solution of containing sodium ions. Now, if you're using aqueous solutions, which means I have water in it, that means I have H plus ions as well, not only this. So if you were to choose between sodium and hydrogen ions, which one would it be discharged? Of course, they would choose, the cell itself would choose H plus. All right, if they choose H plus, then the main thing that produce is actually hydrogen gas, not sodium, right? So write the half equations for the reaction that occur instead of the production of sodium. So the half equation is the productions of hydrogen. Hydrogen ions plus 2E, right? You're getting hydrogen gas instead of sodium metal if water is present, right? That's for E. Okay, F. Alumina, or so-called bauxite, aluminium oxide. That's the ore of aluminium. Dissolved in molten cryolite, okay, is used in preference to molten alumina in electrolytic productions of aluminium. Why do you need to dissolve in molten cryolite? Because cryolite reduce the melting point of alumina because it needs to be in molten state. So if you put into cryolite, it makes it easier for the alumina to be melted into in molten state before the electrolysis take place. So basically, they are trying to ask what is the function of the molten cryolite. It's just to reduce the alumina, the melting point of the alumina, or another reason is alumina, the cryolite is actually help to increase the conductivity of the electrolytes because cryolite is also ionic compound that contribute free moving ions. All right. Okay, last questions. Now, Faraday constant is defined as the charge on one mole of electrons. Wait, this is the last question, right? Okay, as usual, um, I will put these things as questions that we're going to discuss in tutorial. Okay, next week. So yeah, please try this after you have gone through question 1 to question 13. I'm sure you are familiar with the formulas and the type questions they ask. So this is a combinations of everything. The last questions you have to explain a little bit why the Faraday constant is not 96500 but higher. So you have to think about one possible error. This is what I'm focusing on. The rest, I'm sure you can solve it because it's similar to the previous questions, all the previous questions. All right. So questions 12, I'll leave it to you. All right. And this is the last one. I'll see you again in the live session. Right. Thank you, guys.